So there's this little riddle that says, if an optimist sees a glass half full and a pessimist sees a glass half empty, how does a chemist see the glass? Well, the chemist is going to see the glass completely full because it's half full of liquid and half full of gas. So this section, we're going to look at what solids, liquids, gases, and even plasmas are. So all four of those are what we call states of matter. And a state of matter is different forms in which matter can exist without the chemical makeup of matter changing. And there are actually four states of matter, and they are solid, liquid, gas, and plasma. And so we are going to take a look at all four of these now. So a solid is a state of matter that has a fixed volume and a fixed shape. This means that the volume won't change and neither will its shape. So for example, salt and a chemical compound called cellulose have what we call crystalline structures. And so those are shown in these pictures here. A crystalline structure is a very, what we call geometric pattern, like a square or a cube. And then steaks and wax are what we call amorphous solids or shapes, and this is basically shapeless. There is no set shape for either of these, and the particles have no definite pattern. In a crystalline structure, the particles are going to have a very definite pattern, and you're going to be able to predict where the next atom or molecule will go. Liquids, the state of matter, they also have a fixed volume, but not a fixed shape. The shape of the liquid will take the shape of the container, and so that we show with this diagram here. Both of those have the same amount of liquid in them. However, the shape of that liquid is markedly different because of the different size and shape of the container. This brings up an idea of surface tension, and we see this especially with water. Surface tension is a force that pulls particle at the exposed surface of a liquid toward the other liquids. So we see this with our raindrops or any type of water really. They kind of have this curvature to them, and that's because all the water molecules are being pulled towards one another. With liquids, we also talk about viscosity, and viscosity is the resistance of a liquid to flowing. Thicker liquids are more viscous than thinner liquids, so like honey is very viscous compared to vinegar. Our next state of matter is gases, and these state of matter has neither a fixed volume nor a fixed shape. Both the volume and shape are dependent on the container, and the gases will spread out to take up all of the available space. So it's important to notice or talk about that when we talk about container, we're not talking about like a Tupperware container per se. Gases occupy really, really big containers, such as a classroom. They can occupy much smaller containers, like this bicycle tire. And so just when we use the word container, don't limit your thoughts to your grandma's Tupperware containers. Lastly, we have plasmas. Plasma is a state of matter that doesn't have a fixed volume or a fixed shape, but it contains ions. This is what makes it different from a gas. So these ions allow it to conduct electricity and respond to magnetism. This is the most common state of matter in the universe. And oftentimes we know it's present because it will glow with light. It can be naturally located, such as in the sun and other stars, lightning and the northern lights. Those all have plasma in them. Or we can have them artificially created, such as with our fluorescent lights, our plasma TV screens, or plasma balls. All of those incorporate plasma. So energy is the ability to cause change in matter. So all of these states of matter can change when energy is present. Kinetic energy is the energy of moving matter. So if matter is moving, it has kinetic energy. And that brings about this kinetic theory of matter. This is a theory that states all matter consists of constantly moving particles. And so we'll take a closer look at that. So particles of the same substance are attracted to one another. So this tends to pull the particles closer together. This requires a lot of kinetic energy to overcome that force of attraction. It's like a tug of war. The particles want to be close together, but there's energy that wants to pull them apart. So the kinetic energy of individual particles versus the force of attraction between different particles. And the winner, whether we break apart those particles or keep them together, will depend on the state of matter. So with solids, the particles don't have enough kinetic energy to overcome the force of attraction between them. So that means the particles are packed very closely together and they cannot move around. It's more like their movement represents some type of vibration. Liquid particles have enough kinetic energy to partially overcome the force of attraction between them. This allows them to slide past one another, but not completely pull apart. And then lastly, gas particles have a lot of kinetic energy, and so they can completely overcome the force of attraction between them and move far apart. So gas particles are constantly on the move, whizzing past each other and just bumping into the edges of their container into other particles. So this diagram kind of gives you an image. So as we move to the right, our kinetic energy is increasing, and same with particle motion. And so solids have very low kinetic energy, where gases have very high kinetic energy, and liquids are right there in the middle. Same with their particle motion. They have low particle motion, or solids have low particle motion, where gases have really high particle motion, and then there's liquids somewhere in the middle. The purple arrow goes the reverse direction, and so that tells you that gases have a low force of attraction between their particles, and that solids have a high force of attraction between their particles. And again, liquids kind of are just hanging out there in the middle.